in the case where I have 2 point charges, and I'm looking at the electric field at some point P in space, happily, we have the easiest possible result. Well, the easiest possible useful result. That, if I have Q1 that's providing, okay, some electric field E1 at that point, and charge Q2, is providing some electric field E2 at that point, then the net electric field is just equal to the sum of those other electric fields. Now, and referring back to one of the reasons why the first semester is a prerequisite for this, part of the stuff that I have to assume you know coming in, is that if I want to add two vectors together, like here, the electric field in this case is equal to E1 plus E2, I have to know that if I take that, what defines E2, for example, is the direction of E2 and the magnitude of E2. The starting point does not matter. So if I draw in this case, I'm doubling E1, but it doesn't matter. E1 plus E2 is the same thing as E2 plus E1. Both of these vectors, well, barring my ability to draw parallels, if those two vectors have the same length and are pointing in the same direction, they are the same vector, period. And when adding vectors, if I have E2 plus E1, which is, double check this, drawing this in a different direction, it's the same as E1 plus E2. In the case of addition, the order of operations does not matter. I simply start that vector sum, in this case the net vector E, at the beginning of one vector, and as long as I've got the vectors lined up beginning to end, then the net electric field is equal to the sum of those two. And if I happen to have that in component form, then E1 plus E2 is equal to E1 in the x direction plus E2 in the x direction plus E1 in the y direction plus E2 in the y direction, and that finds a component in, surprise, the y direction. Very helpful, hopefully very straightforward, and yet it's going to lead us to a great deal of useful circumstances.